matrices. Determinant. So therefore, hopefully you guys just did, there we go, x plus 4 times x minus 5 as your main, right? Minus opposite, minus negative 14. Are we good? All right. So we end up with x squared minus 5x plus 4x. Anybody get negative x minus 20 plus 14 equals 0? At this point, did they just basically think up a tricky way for you guys to have to practice factoring? The answer is yes. What do you guys get as your factors? X minus 3 and x plus 2. So therefore, are there any restrictions in matrices as to what the x values can be? They just have to work. Positives, negatives, zeros, I can have them all in a matrix, right? What are some functions, though, in the past that we've been restricted to, where we had like extraneous solutions? We had to be careful that the answers really were legal. Logarithms, yeah, that's the key one, because logarithms, remember, only work for what kinds of values? The domain of a natural log or any log of x. Positive numbers, non-zero positive numbers. So if we were to get like an x equals 0, or a number when plugged in that gets 0, or a negative number, or a number when plugged in that gets a negative inside a logarithm, that's where you have extraneous solutions. But it's just good for your brain to remember, especially because there's a final eventually. In math, when we can bank on the solutions. Because isn't that kind of important in math? Let's make sure we're not distracted. Okay. It's important in math to know, like, hey, I solved it, and I'm done. And it's right sometimes. Usually it's right all the time. We just have to be careful of a few tricky functions like logarithms. And sometimes like square roots also, since they have a limited domain. All right, cool kids. Let's go grade 8 for determinants. Number 6 should have been negative 10. Number 16 should have been 34. Number 44, you were supposed to do it 2 different ways, but my question to you isn't so much if they both worked, because I think you guys knew they were supposed to both get 64. Which one did you think was easier? Because you chose 2 very different rows/columns. This one you were choosing row 4, which only had 1 0 in it. And this one you were choosing column 2, which had 3 zeros in it. What was nice about the first one versus the second one, or the second one versus the first one? And literally, it really is just you guys kind of getting familiar with matrices to the point at which you can have preferences. But what was nice about choosing the row with not very many zeros? You had to do 3 different things still, right? You had to figure out 3 different numbers times, because this was the only one that canceled out to be 0. But once you got here, what was nice? Couldn't you choose a row or column with lots of zeros in it? 6 or 1 with a negative 2, and then a little baby. The mental math was pretty easy on the 3 that you had. What was different with this guy down below? How many things did you get to ignore altogether? Oh, a lot of them. 0 times, 0 times, 0 times. But what was true about this guy? It was somewhat easy, but you didn't have as many zeros as far as for each individual. So you would have had to choose a row or a column that at most would have only had 1 0. And so you could have done like this guy, but then you would have had that guy and that guy to ignore and then take what was left, etc. What's a bummer about the answer key? What are they not showing you? All the in-between. Yeah, Gavin.
So what is that rephrase? So do you do where after you get to the 3 diapers, is that then when you circle one of them?
Yeah, you have to go again. Yeah. So like on this one, just for an example, right? Where did this negative 12 come from? Because there was some work that was necessary. Where did you guys get the negative 12? Did you choose the first row or the first column? Hopefully you chose one of them. There's 2 zeros, which is nice. First column, okay. Times plus 0, well, technically, that's a positive, a negative, a positive, right? So technically, 0 times, it doesn't matter. Whatever, it doesn't matter. It's good. Times. So then, Gavin, we would have done our little like cross, and then had 0, negative 6, 1, negative 2. You have 0, minus a negative 6, so 0 plus 6 is 6. 6 times a negative 2 is negative 12. So that's the work they're not showing. Does that make sense? Or in their heads, they could be doing our shortcut of rewriting those two columns and doing main, main, main minus opposite, opposite, opposite. But either way, they're not showing that work either. Yeah. Anybody else get stuck in the work? Calc chat didn't show very much. Are we okay? Okay. Let me know if you get stuck somewhere. Because you wouldn't have necessarily been able, you could have seen what the number should have been after all of your work as far as what should have been multiplied by negative 3, right? But as far as how to get there, that was a little rough. Okay. 56, they told you which row to expand along. So the nice thing is they totally showed their work on this one. 3, you have a little 2 by 2, 0 is a little 2 by 2, 0 is a little 2 by 2. But remember, 0's, well, 0 times anything, doesn't matter. 22 minus 0, negative 3 times 22 is negative 26. This one, they showed their work nice and neat and clear. Negative 66, final answer. Number 62, they used column 1 and then column 1 again. Why? Because they were like, we love the zeros. No, it was a 5 by 5. This problem was so mean. Wait. But don't you just take the 5 and then take who's left? And then all the rest is 0? And then can't you just take the 1 and take who's left because all the rest are 0, right? And then, okay. Oh, can't you just use the bottom row? Which would be 0 plus 0. Well, it's technically plus minus plus. 0 minus 0 plus 2. 2 times what? 8 minus 18. 8 minus 18 is negative 10. 2 times negative 10 is negative 20. Booyah, done. Okay, maybe you should have shown a little bit more work than they did. But do you see how we love rows and columns with zeros? Could have also chosen, if you really wanted to, you could have chosen row 5 instead of column 1. And then number 86 was super similar to what we did at the beginning of class, true? It was just even a little bit easier because all you had to do was distribute and then minus opposite, so minus 3, and then factor. Dun, 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 dun. Dun, dun. Do we have any more evens that you guys can see? I want to scroll down, but a few people are still checking their work. Something went wrong. Any more evens? Okay, cool. Any questions on the odds while I give people just a second more with the answer key? Odds or evens? Sorry, I apologize. Odds or evens? You sure? Give me a thumbs up if you're good. Give me a thumbs middle if you're like barely here, and give me a thumbs down if you're like, I hated the whole homework and I'm so lost. Ready, set, go. No, no, no. Look at me, look at me, look at me, look at me. Let people do whatever they need to do. Cool, cool, cool. Kim's still wondering about life. Okay. I didn't see any thumbs down. I see some thumbs middle where it's just like, I'm trying to hang in there. I don't know if it's determinants or if it's life, but if I can help with either one, please let me. Or please at least come. I can try to encourage you. If you're starting to not feel so well, please just wash your hands really well and try not to cough on people, which is what I'm trying to do. And get sleep tonight. Okay, questions. Sorry, Adam.
62.
Yeah.
It's the 5 times 1 of the determinant of 2 factored by 2.
Yeah.
Could you go through that, doing like
Here?
the method where like you add the 2 columns?
Yeah. What Adam noticed is right here, it was a 3 by 3. So whereas I went with row 3 and I said, oh yay, 0 minus 0 and 2, and I did my little 2 by 2, so I kept going with expanding cofactors. Adam just wanted a quick refresher as if you were to do the shortcut. So the shortcut, remember, we need to be able to go 3 times main and 3 times opposite, which means 1, 2, 3. I need 2 columns repeated, so 2, 3, 0. You see it? Some people might have forgotten this was a thing. You could do main 16 plus main 0 plus main, nice, minus, now careful, all of this needs to be multiplied by 5 times 1. But then we go the opposite way, right? 18 and 2 is 36, 0 and 0. So then I have 16 minus 36, which is negative 20 times 5. Dun, 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 dun. Nice. Okay, we good? Okay. Life is a little rough for some of us. Determinants might be a little rough for some of us. Hang in there. We're trying to tackle these things as they come. But I'm hoping today can at least be a little fun, because what did I say was coming at the end of the... I didn't say easier stuff. I said applications. Wait, no, you didn't say applications. No, I didn't. I'm totally lying right now. I did not say applications. What did I say? Coding. There we go. Coding. Does this look like coding to you? Looks like formulas. Okay, applications of matrices. Applications of matrices don't start with coding, they end with coding. Applications of matrices aren't starting with coding, they're ending with coding. So hang in there. It's not going to be the very first topic. We might not even really get to it much today. But tomorrow, if we don't get to it today, we will definitely be playing with cryptography, with matrices. There are lots of ways of encoding messages. There are lots of ways of encoding messages. But matrices are kind of a snazzy way. Because matrix multiplication is so complicated, you have to multiply, remember, each entry of a row by each entry of a column, and then you add them all up. The numbers get so mixed up. Well, you'll see it when it comes. But first application of matrices. And not that we're going to cover all of them. There's actually a class in college called linear algebra for engineers, for computer programmers, for math majors. I'm not sure who else exactly takes it. Any sort of tech related would have it, though. That's all about matrices. So if there's a whole college class about matrices, well, I don't think we're necessarily covering everything in one section in Honors Pre-Cal, right? But you get a little peek of at least a few uses. If matrices are something that can be programmed, how they work, how to multiply, how to add, how to subtract, how to find the inverse, how to solve systems of equations. Wait, that's an application we haven't even talked about. Row reduced echelon form, I mean, we've done it. But it's not going to show up in this section because we've already used it for those things. Matrices can be used for more. And not just matrices, but determinants. So far, beginning of class, you guys saw that determinants could show whether or not a Sudoku puzzle is possible. If you had an answer key of a Sudoku puzzle, and let's say it was 100 by 100, and you're like, oh, stink. Can I really keep track of all of these numbers and whether or not there was a repeat in some random row or column? No, but you could find the determinant and see if it's 0 or not. If the determinant is 0, it's an impossible puzzle. Something accidentally got messed up. Okay. Well, that's one silly application. Huh? Wouldn't that be? Yeah. Which I don't know who would possibly want to do that. I wouldn't. But I was just saying, because you guys have seen Sudoku puzzles that get bigger and bigger. But usually they just get harder and harder by taking out more and more numbers. And every now and then there's more than one solution, which is really mean, of the really hard ones. Bum-ba-dum. Okay, nice thing in section 8.5. I want you guys to make a note really quickly. Everything in 8.5, most everything you can use your calculator on. I think Kramer's rule is the one exception to that. Second. I think I put that wrong. I would say using a calculator if I wasn't too lazy to erase it. You can use a calculator for almost all of the section. Okay, Kramer. How to use determinants to solve a system. Do you guys see how we have a system of equations with two unknowns? And all of these are just numbers. They're just constants. They're just placeholders. Kramer's rule says to find x and to find y, you can actually use these formulas, which would look quite complicated if you see them, right? These formulas look pretty nasty. X equals, y equals, ugh. But wait, isn't this just a main minus an opposite? Isn't this just a main minus an opposite? Isn't this just a main minus an opposite? And a main minus an opposite? These are just determinants. But where on earth are these matrices coming from? This is where it gets a little weird. Where on earth? Now, hold on. Provided that, why can't the denominator be 0? Oh, that's easy. You can't divide by 0. So guess what would happen if you ever got this denominator to be 0? No solution. It'd be one of those inconsistent systems. So right away, we just figured out with a determinant, we can know whether or not a system of equations is possible to solve or not. But wait a minute, hold on. Where did these matrices come from? Guys, look at these denominators. The guys who can't be, or the determinant of which cannot be 0 in order to have a possible solution. Where did A1, A2, B1, B2 come from? They're the exact same denominator. Where did it come from? The system, and specifically what part of the system? So if I was to try to summarize Kramer's rule, what I could say for each of my variables is, for a particular var, for a particular variable, I'm going to go ahead and take the determinant of the coefficient matrix. Coefficients are the little guys, the little numbers, the numeric coefficients of my variables. So the determinant of the coefficient matrix, so A1, A2, B1, B2. I guess I should read it the proper way. A1, B1, A2, B2. Those are my denominator. But what's going on in the numerator? Those are very different matrices. Can you guys see a pattern? There's a very definite pattern as to where that numerator comes from. If you're looking for x, you move. I like that. I like you move. Do you see it? If you're solving for x or y, you move the C1, C2, but where? For x, where do you move the C1, C2? In place of whose coefficients? And for y, where do you move the C1, C2? In lieu of or in place of the... Oh. What if this was an XYZ system? Do you think that Kramer's rule could still be used? Yeah. You would have the coefficient matrix, which would now be A1, B1, C1, A2, B2, C2, and then there'd be like a D1, D2, D3. You could still have a coefficient matrix of a 3 by 3, and you would just take out the x's, put in, take out the y's, put in, and then take out the z's, put in. So let's see how we can kind of reword that to make it a little baby formula that we can, in a sense, study. So we're going to have a determinant of, we can do the coefficient matrix, right? However, can I put replacing the vars, what would that be? Column, right? Column with, what do I mean by SOL? Not sun in Spanish, but the solutions, right? So coefficient matrix replacing the vars column with the solution column. And then you solve. How? Oh, just using determinants and then having a fraction. Now some of you might be like, there's no way this is easier than elimination or substitution. I loved section 7172 and it never got tricky. Well, there were some ones you didn't like way back when, especially when there were fractions involved. So there are a little, like, you could make another way of writing this. I don't know if we necessarily need to write out any more formulas. I think we're good with what we have, huh? So let's go ahead and try this guy. Now, I'm not saying this guy is an easy or a hard solution. Maybe he's easy, maybe he's hard. But I want us to try to use Kramer's rule to solve. Okay? I want us to try to use Kramer's rule to solve. Now, if I totally thought through this, I might have a race right now, and you guys could solve with elimination or substitution. I solve with Kramer's rule. But I do want you to practice. But if you want, you could try to solve really quickly substitution or elimination and then try to check it with Kramer's rule. I'm going to go straight Kramer's rule. So I give you the option. If you want to try to bust out with substitution or elimination or row echelon form, man, I'm giving you so much head time, though. Lead. All right, I'm going. People that like mental math, this is actually kind of a nice numeric way of solving for solutions without ever dealing with the algebraic expressions. That's kind of fun. That's kind of cool. I want you guys to really quickly discuss in your groups. First of all, is anybody back to Nice, 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 nice. What did I stop writing? And how did it get me in trouble? Yeah, I stopped writing the negative, right? Ooh, it wasn't even necessarily a mental math mistake. It was just a rewriting mistake. Okay, good. Now are we good? There you go. Ready, set, talk it out in your group. Did you understand where Kramer's rule or how it was used? Because I'm about to come up with a nastier example. You guys ready? There's for a purpose. There's going to be a competition in just 1 second. All right, you guys ready? I found the solutions only for the purpose of me being able to know whether or not I was right, but I'm not going to look at it the whole time until I write down, I'm just going to write down the system. You guys ready? I want you to use Kramer's rule, or actually any rule. You can use elimination, you can use substitution, you can use row echelon to solve the following. Whatever you think would be fastest. I'm going to do Kramer's rule. I want you to use substitution. I want you to use elimination. I want you to use row echelon form and see if you can beat me. You guys have the system down? I'll be fair. I'll be fair. Next. Get set. You're going to do substitution, elimination, something, something, something. See if you can beat me. Ready, set, go. Just pondering how awesome that was as some of you guys are having fun. Aren't you done yet? Using substitution or elimination? If you guys tried substitution or elimination, I did elimination. Do you see how nasty this is? If you did elimination, I multiplied the top by 5, the bottom by 7, then I ended up with x equals 22 over 73, and then we have to take 22 over 73 and plug it in. We get a complex fraction that needs common denominators. I ended up with 175 over 511, and somehow we should have factored that down or reduced it to 25 over 73, as opposed to Kramer's rule that said, no plugging in of fractions necessary, no reducing necessary, done. Nice. Kind of nice. Unless you hate numbers and have a fear of them. It's amazing that you've gotten here to Honors Pre-Cal, by the way, if you have a fear of numbers. No, it truly is, like completely and absolutely. That's really cool how hard you've worked. But other than that, most of us at least are pretty okay with numbers. And I like that a whole lot better than the nasty elimination I did on the board just to make sure I was okay before I gave it to you. Because that, right there, bleh. Kramer's rule. Nice for really nasty systems. Okay, boop. What else do we have? A 3 by 3, is it possible? Nope. Is it possible? Yes. I'm not going to have you guys actually solve by hand the 3 by 3 with Kramer's rule. I'm just making sure you understand the process. So can we just write out what you would use to find x and y and z, just to make sure that we're totally solid on the process? Okay. What would you use for your denominators of every single one? You guys grab out your calculator. We'll get some numbers to plug and chug. Is that cool? I'm writing down the coefficient matrix. I'll have you guys with your calculator for sake of time. You don't need to watch me do a determinant of a 3 by 3. That was so section 8.4. Get me the value of the denominator. Yeah, kind of, right, Robbie? It was yesterday. Oh, dear. Oops. He's like stuck there. Yeah. We'll just get rid of him. You're getting me the determinant of the coefficient matrix, because we'd have to use him for everybody's denominator, right? You wouldn't do it 3 times. Hopefully you know you would only use it once. Adam has a determinant of what? 33. Anybody want to back him up? Sweet. I already have the denominators of all 3 of my solutions, and that is gross. Okay, how would I do my numerators, though? What matrix would I use for x? Negative 14, but yeah. Because all the x coefficients come out. Excuse me. The solutions go in, and then I have to rewrite the rest of the coefficients, right? And then 1, negative 2, 1. Okay, how about for y's? What matrix would I use? Yeah, I'll go down. I'll go down. Negative 1, 3. X's stay in. Who comes out? So what goes in lieu of or in place of? But I still keep my z. Maybe some of you guys can be finding determinants of some of these. My z's, I keep my x's. But who's out this last time? The z's. Booyah. Kathleen.
So how did you write out those things?
It was using that little trick that we tried to put in words. It's just kind of hard when it changes every time. But the trick that we put in words was the numerator is the coefficient matrix, but replacing the column of whatever variable you're solving for with the solution column instead. So for x, we took out the x coefficients and put in the solution instead. And for y, we took out the y coefficients and put in the solution instead. So with the one we just did, we're taking the coefficient matrix, He's our denominator. But for each one, when I go to solve for x, I take away all the x coefficients and I put in the solutions instead, which is why those were there and everybody else stayed the same. And then the y's disappeared with the solutions going in instead. And then the z's disappeared with the solutions going in instead. Whoop! There's a smartboard right there. Kyle.
So when you're solving it, do you find the determinant of that and divide it by 33?
Yes. But what do you have for the numerators? Because maybe they're actually kind of nice at the end of the day. Because what's the first one? 0? Then 99? Oh. Kramer's rule will always work for solving a possible system of equations. Remember, the only time it's going to be impossible is when the coefficient's determinant is 0. Would that be nice to have had a way at the very beginning of all of those problems, those systems we were solving, to have a way to know whether or not it was possible or not? Yeah, it would have. If we could have found one determinant that tells us, yeah, go for it, there are solutions, or nope, hey, just kidding, it's going to be infinitely many. That might have been nice at the beginning. The determinant of the coefficients, if it's non-zero, go for it. There will be an answer. If it is 0, oh, infinitely many. But this one, guys, it might have been easier to solve another way because these numbers would have been pretty nasty and your solutions were pretty nice. But remember, in the last example, well, I would have beat all of you with elimination if you guys had all done elimination. Any other questions before I move on from Kramer's rule? Application number 1. Let's go. Application number 2. Area of triangles? What? You can use matrices and determinants? Without having to memorize a nasty 1/2 BC sine of A, law of sines version, or square root of s times s minus a times s minus b times s minus c, Hero's formula or Heron's formula, where s equals the perimeter 1/2 of a plus b plus c. You could just throw in your 3 points with the third extra random column of 1s and find the determinant times 1/2. Plus or minus. Area is never negative. Exactly. So if this value is negative, long story short, make whatever you get positive. So application of this, if you were to be given 3 random points, you don't even need to know the side lengths like you would for the Heron's formula. You would have to find 3 different distances and then go use Heron's formula. Oh, that's stinky. Or you would have to go find angles somehow. How would you find angles? Maybe law of cosines after you find the distances, then you can find an angle, then you can use the other formula. Or you could just say, I can do matrices. Area is equal to, plus or minus, we'll figure it out in a second, 1/2 of, take your 3 points in absolutely any order and plug them in. 1 and 0, 2 and 2, 4 and 3 are the points I see on my graph. You do a third column of 1s. All you got to do is find a determinant. I'm going to use row 1 just because I'm cool like that. Zeros. Plus or minus, I don't know yet. 1/2 times. 1 would be multiplied by the 2 by 2. You guys okay if I do in my head? Now, I know I'm about to go a little crazy. Are you okay if I do like a main minus opposite and I see exactly what main minus opposite I'm doing? 2 minus 3 is going to be a -1. I can be calc chat for a bit. Is that okay? 1 minus 0 times, it doesn't really matter, plus 1 times, just this time I'm taking 6 minus 8. I know, I did a little bit of calc chat mental math with matrices. Don't totally hate me. You know how to do determinants from, whoa, section 8.4. And we get -1 minus 2 is -3. Aw, that's a negative number. That's okay. Then we'll steal the negative and say, haha, I need you to be positive, please. A negative times a negative is a positive. Done. Just always make your area positive. Wait, actually done? Yep. How could you check me? Throw this guy into your calculator and check his determinant and multiply him by 1/2 and make him a positive number if he's not already. Well, that sounds kind of nice. Well, you can also figure out collinear points. How? If 3 points are on the same line, what is that going to mean about the possible area of a triangle that connect? Wait, if 3 points are on a line, do you even have a triangle? Don't you need 3 points where one of them is non-collinear, or where they're not all collinear, I should say? Are these 3 points all on the same line? I don't know. What could we do? We could say the area would be 0 if they're not able to make a triangle, and the only way they can't make a triangle is if they're all on the same line. So we would take these 3 little guys and we would go ahead and plug them in and say, okay, well, if I was to plug in -2, -2, and 1, 1, and 7, 5, with a third random column of 1, all I need to do is say, is your determinant 0? If it is, you're collinear. If it's not, you make a triangle. You can't possibly be on the same line. Once again, my job today is not teaching you how to do determinant. Oh, hey, I already have it written. That's okay, I just did it. So then there may be a way to use a determinant to find an equation of a line passing through points? How? Because you say, okay, I have 2 points. Sweet, that's all I need. Let's just throw in a general x, y. 10, 7, -2, 7, and x. And say, I need you all on the same line. What? That's a thing? Yeah. That can be a thing. I'm going to use row 3 just because it looks nicer. I'm going to do this one because it has an x and y. That's kind of mean. That's not really 8.4. I think that's kind of up. So I'm going to go ahead and do my 1 times. Main would be -2y minus opposite would be 7x. Positive, negative, minus 1. Main, 10y. Main, 70, minus -14. It's equal. It's -2y minus 7x. 70 minus 84. I end up with -12y plus 0. Into standard form too, which is kind of nice, as opposed to having to get slope-intercept and then make it standard. Oh, we should have been able to figure, wait, -7, sorry. -84 divided by -12 is a. Oh yeah, because they both share 7. It had to have been a horizontal straight line.
Wow.
I was going to say straight line. Y equals, you can fly. It's a horizontal line. Oh my goodness, so many applications today. We talked about Kramer's rule, how to solve a system of equations. And we talked about area of triangles. And we talked about collinear and equations of lines. So what is left for us to do? Assign every letter in the alphabet. I know it's kind of awkward. It goes 1, 2, 3, 4, 5, 6, 7, 8, and then it goes, I know. It just is what it is. But assign every letter in the alphabet to a number. Oh, we can code messages. We can say H is 8 and I is 9. 8, 9. But someone could break that down pretty easy because, like, I'm pretty sure you just made A1, B2, C3. You could make it a little bit harder and make maybe all the odds be letters, but then they should notice that because, like, well, there are no evens in your message. That's weird. You could have it be like every 5 or every 6 or every 7, but even then they'll eventually realize, oh, it's only multiples of this or that or the other. How can you truly mix, where 1 second, even though D was E, with matrix multiplication, E can be 10 different numeric values because a matrix mixed it up. We'll see how that works tomorrow. Guys, you can do up through, what, 40s? 50s? Go, team. We'll work on cryptography tomorrow. Huh? Oh, sorry, not tomorrow. Thank you, Thursday. Awesome. I couldn't remember what day today was.
I hope Thursday.
Thursday. Oh, I never announced it.
Can I?
Yeah.
It was hot today.
I know. It's rough in here. I almost took off my.
Hard to stay awake.
I'm sorry.
But I stayed awake the whole time.
You just kept answering. It was good. Tomorrow we'll be encoding. It'll be fun. You guys will be mixing up messages and passing them around. Appropriate messages. Appropriate.
How hard is the message going to be on the test?
Every year I change it. Oh, who knows?
I have something hard to explain. So yesterday,